All right, time to talk about that total internal reflection that I mentioned in the last video. So total internal reflection, it's actually something I did on the example problem we did back on April 29th, or April 30th, sorry. So it's been a little bit, but that's where we're going with this. Now, total internal reflection is going to be abbreviated TIR. Whenever you write TIR, I know what that means. It's a common abbreviation. So the idea is that total internal reflection occurs because the light is bending so much, it actually stays in the original medium. It doesn't go out into that new space where it was before, where it's trying to get to. And you can kind of see that in the video that are in the picture here, and you have an example of that as well. Now, the two red ones are the ones I want you to look most carefully at on the screen. The one that is just skimming the surface, that's what I was talking about with the idea of critical angle, that it's that's that maximum angle of incidence that will allow it to just skim the surface. If the angle gets any bigger, it doesn't refract. It doesn't bend as it's leaving. It stays inside. It's bent so much that it goes back inside and follows the law of reflection, okay, instead. So that critical angle is what we're going to be really focused on. And you have that defined for you already. It's the angle of incidence that causes the angle of refraction to equal 90 degrees. Okay, and we can determine that using Snell's law. To keep life a little bit simpler, we have the formula that the critical angle is equal to the inverse sine of NR over NI. The thing you need to remember or realize is that total internal reflection and critical angle can only occur if the refracted medium, the N value, the optical density or index of refraction for the material you're trying to go into, is smaller than the material you're trying to leave. Okay, so if you are trying to go, and that's when the light is bending away from the normal line, okay? So that it happens when you're trying to leave water, but not when you're trying to leave air, okay? So you have some practice, you have a practice problem with this. Total internal reflection is actually part of the reason why a diamond is as bright and shiny as it is, because light actually gets trapped inside that diamond. Okay, now at every barrier that you come to, and you saw this in that Snell's Law lab that you were practicing with, you're going to have the incident light, the starting light, oh my gosh, sorry about that. The starting light, incident ray, goes into the material, it goes into the barrier, and then it kind of splits. Some of it gets reflected and stays in the original medium. Some of it gets refracted and goes into the new medium. How much is which depends on the barrier, and quite honestly, depends on that angle. Okay, what is it you're bouncing? What is it that you're bouncing into, and what happens there? All right. So you have a couple of problems to continue working on. I would check those, and you should check back tomorrow for solutions with that. Thanks.